All right, 3 different kinds of reactions in the beginning of this module. We have formation, decomposition, and combustion. We have already looked at decomposition. A decomposition reaction is a reaction which takes a molecule and breaks it down into its fundamental forms. In this case, silicon, you've got SiH3F as a molecule. It's going to break down into the different elements of Si, H, and F. When you have a decomposition like this, we said what's the first thing we're going to look for in the products of decomposition? What are we going to look for? Okay, but even before it's balanced, we need to recognize, and I encourage you to look for homonuclear diatomics. Okay? Because we can do all the balancing we want, but then if we go, oh, but wait a minute, that's a 2, not a 1, it throws the balancing off. So we look, is silicon a homonuclear diatomic? No. Hydrogen? Fluorine? Okay, so now we have our homonuclear diatomics. Now we can start going through and balancing it. We're going to use the shortcut rather than the long matrix, okay? Because I think you guys have now understand about how to balance the reaction using the matrix. Okay, but we'll use the shortcut method, okay? From here, I have 1, 1, 3, and 2. How do I get 3 from? I have 3 and I need to use them up in sets of 2. How many sets of 2 do I need to get 3? Yes, I need 1.5. Right? 1.5 sets of 2 is equal to 3. And I have 1. How many sets of 2 can I make from 1? How many sets of 2 can I make from 1?
Teaching her about homonuclear diatomics.
Oh, okay.
So it's about chemistry.
Okay.
The line. I told you there was a line.
So we have 1, 1, 3, 3, 1, 1. Everybody see that? This is a form of my balanced reaction, but it's not an appropriate form, right? We need to get rid of the fractional coefficients. So how are we going to get rid of the fractional coefficients here? Good. Multiply everything by 2. So we're going to multiply the entire thing by 2, and it's going to produce a reaction of 2 SiH3F decomposes into 2 Si plus 2 times 1.5 is 3 H2 plus 2 times 1/2 is 1 F2. Let's check it real quick. 2, 2, 3, or excuse me, 2 sets of 3 is 6, 3 sets of 2 here is 6, 2 sets of 1, 1 set of 2, it's balanced. That's a basic decomposition reaction. Taking a molecule, breaking it down into its constituent forms. Balancing the equation. And let's see, is there anything else we want to make sure we cover? Again, this is review. We did this one before. Mm-hmm.
So if I was to circle answer, just circle that balance equation?
Yeah, this is your balanced this is your balanced equation for a decomposition reaction for this molecule, SiH3F. Okay. Are we still talking homonuclear diatomics? Because the conversation's expanded. I thought maybe the whole class should get involved in it, because it's only 2 of the 4 rows. Wait a minute, that's half the class. I can do math in my head. 2 of 4 as 1 is to 2. Yeah, it's half. All right. So we've got decomp. We've already done it, and now we've reviewed it. What do you think a formation reaction is then?
What is it? Just a decomposition switch?
Yeah, it's the opposite of it. Rather than having a basic way of looking at a decomp would be ABC produces A and B and C. A formation reaction is A and B and C react to produce ABC. It's just the other way around. So if the question, like in example 7.2 says, write the chemical equation for the formation of MgCO3. Are we still talking about homonuclear diatomics? Okay. Homonuclear diatomics, they are elements that naturally form as molecules rather than individual atoms, and they're found as hydrogen as the one exception, and then nitrogen, oxygen, and the entire column 7A elements. Are there any more questions? Good, let's move on. All right, what is the formation reaction, or excuse me, yeah, the formation reaction for MgCO3? Well, I'm going to set up a reaction that produces what I'm trying to form, my MgCO3. Okay? So this is what is the formation reaction for MgCO3? That's going to be my product. Go through and break down for the fundamental components. What are the elements that make up MgCO3? I've got magnesium and carbon and oxygen, right? Next step, same as in a decomposition. What am I going to do? Look for homonuclear diatomics. Is magnesium either hydrogen, nitrogen, oxygen, or column 7A elements? No, it's not. It is carbon hydrogen, nitrogen, oxygen, or a 7A element? No. Oh, is oxygen a hydrogen? Oh, it is. Okay, good. Just trying to reinforce learning here. So oxygen is a homonuclear diatomic. Now let's go through and balance the equation. 1 and 1 balances. 1 and 1 balances. 2 and 3. Doesn't balance, does it? So I need to change my coefficient. I'm going to change my coefficient in my reactant side since I have the fundamental forms over here. I'm going to add a coefficient to my oxygen. Give myself a little space here. I mean, how many sets of 2 do I need in order to get 3? 1.5. Very good. That's a balanced form, but it's not, we're going to say it's true but not correct for this class. We need to have full integer coefficients, so let's go through and do something to get the full integer, and in most cases, as you know, it's going to be multiply it by 2. Multiply the whole thing by 2, and we end up with 2mg plus 2c plus 3O2 reacts to produce 2mgCO3. Okay, so it's the same as the decomposition, except it looks backwards. You're taking the fundamental elements and combining them to produce a molecule. In a decomposition, you take the molecule and you break it up into its fundamental elements. That's it for formation reactions. Any real questions on that? Remember, hydrogen, nitrogen, oxygen, and the 7A elements. Get rid of it now. But I can't answer the questions without the black marks. Okay, sorry. Now we get to some fun stuff. Combustion reactions. Combustion reactions, some of them sound like this. You know, like when you're having a bonfire and you go with the white gas and you throw it on. Remember that sound? It's like the concussion. Okay? And there's some reactions that sound a lot like this. Okay? We're going to look at two different kinds of, well, more than two, but two basic kinds of combustion reactions. And the first one we're going to talk about, and combustion is really a reaction with oxygen. It's a reaction with oxygen. We're going to talk about combustion of metals first. They give in the book the example 2mgs plus O2 gas reacts to produce 2MgO solid. Okay. I have been in several of these fires before. It's incredibly hot. It's incredibly bright. especially when you're flying in night vision goggles and looking at it. It's really, really bright, okay? Where have I seen this before? Well, magnesium is the major component in the transmissions of the helicopter I flew in the Marine Corps. And the number 2 engine on the CH-53 Echo is prone to catching on fire. Of all 3 of them, the number 2 tends to catch on fire. The number 2 is married up right against the main transmission, which is made up primarily of magnesium. So when the number 2 engine catches on fire, if you don't get it out in time, it will eventually get warm enough so that it adds enough energy to the magnesium that makes up the transmission that it starts to react with the oxygen in a form that we call burning. The metal starts to burn. And when the metal burns, it releases a lot of energy in the form of light energy and in the form of heat energy. And the product of the reaction takes magnesium, and the burning combustion process reacts it with the oxygen in the air and produces magnesium oxide. Okay? When you have something, and we don't tend to think of metals as burning. Maybe we'll show some videos of people burning magnesium or burning, I think zinc is another one, but where you light it and it flashes, the metal shrivels up, it changes into something different. Its molecular form changes because it goes from being an elemental form into a molecular form of something else. Okay? But you can actually burn metals. There's nothing about wood, books, the desks you're in, up here on the ceiling, the ceiling tiles, we might say, well, maybe they're flame retardant or flame resistant. We tend to think of fuel for the fire. We don't tend to throw metal into a fire, right, to get the fire going. Those are the kind of fires that, you also find half melted bottles, and it's a trash fire, right? Nails at the bottom. Those kind of fires where things turn to ash and some things are metal, and some of the metal might get softened, but most of the metal just falls to the bottom because there's not enough heat. There's enough energy to get this reaction to take place. But if you do ever cross that line and give enough energy to the magnesium that it has available oxygen, it will combust. It will burn and will produce magnesium oxide. So this little section here on combustion of metals is just really here to remind you and to show you that metals burn. There's nothing inherent about a metal that says it can't be used even potentially as a fuel for a fire. The thing with metals is you've got to have a lot of energy in order for them to burn. And usually if you've got that much energy, you're already using that energy in some other heat source, in some other heat form. But a metal, just like anything else, can burn, given the right energy. And remember that burning is fundamentally reacting with oxygen. That's what burning is. The energy to react with the oxygen. Okay. When you burn a candle, for example, it's the carbon in the wick reacting with the oxygen in the air, and the flame you see is the energy being used and produced with that reaction between the carbon and the oxygen to form carbon dioxide and water vapor from the candle. Oh my goshness. Didn't miss that much of the lecture after all. Okay, so combustion of metals. Now there's another one they give in the book on conduction of metals, and this one is very different from the first one. It's 4 FeS plus 3 O2 gas reacts to produce 2 Fe2O3. Now, I said there are 2 types of sounds that go with combustion reactions as well. I was just kind of joking there because I knew we were going to look at these 2 reactions specifically. This first one is more like the, right? A lot of energy, a lot of light, a lot of heat. This one here, what does this actually describe? Look at it. We've got iron and oxygen, so we're producing ferrous oxide. It's rusting. Rusting is a form of combustion. Did you know that? Rusting is a form of combustion because what's happening is iron is oxidizing. That's what this is called. When iron takes on oxygen, it's oxidizing. It's combusting. Now, the velocity, the rate at which it happens, this is so powerful because once you trip that energy level, it happens very, very, very quickly. That's the difference between like lighting a fuse and lighting the black powder at the end of the fuse. Okay? The fuse goes kind of relatively slow. That would be kind of like the ferrous oxide, the iron rusting. It's slow. Not a lot of speed, not a lot of energy being released or absorbed. It just kind of meanders along. But then it goes over a waterfall. Boom. Okay, this is a different kind of reaction. This happens very, very quickly. If you took it over time and said, okay, to completely oxidize both of these things, it's comparable, right, in terms of the actual number of molecules that may get involved with oxygen over a period of time. This may take years. This might take microseconds. That's why this is explosive, because it's the same reaction confined to a very small amount of time, as opposed to a slow reaction, which may express or release the same amount of energy, but it does it over years instead of over milliseconds. So these are both different kinds of combustion reactions. Combustion primarily, again, is reacting something with oxygen to produce the oxide of that element. So the example in the book, example 7.3 for 3rd edition, they say that a butane pocket lighter works by evaporating and then burning the liquid butane, C4H10. Write the balanced equation for the complete combustion reaction. Now, they use this phrase, complete combustion reaction. I've said before that combustion is what? What kind of a reaction is a combustion reaction? Okay. Whatever we're combusting, reacting with oxygen. And oxygen is typically going to be in the O2 form. Okay? So if we're combusting, this case, butane, we're going to react butane with oxygen to produce something. Now, for metals, when they combust, they produce the oxide of that metal. Iron becomes iron oxide. In the case here, where it's a nonmetal, here's a carbon, hydrogen. Hey, what do we see here again? Carbon, hydrogen, oxygen, right? Cho comes back again, back to haunt us. Another carbon, hydrogen, oxygen reaction. But for complete combustions, the definition in the book says it's a reaction in which oxygen, O2, is added to a compound containing carbon and hydrogen. So some molecule with a carbon and a hydrogen. It could be different. It could be, other than 4 and 10, it could be 6 and that might be 12. To be honest with you, I don't know a lot of them off the top of my head. But all of these fuels are carbon-hydrogen molecules. So some relationship, some proportion of carbon to hydrogen is formed, and that is the fuel. When that carbon-hydrogen molecule is combined with oxygen, and it produces carbon dioxide and water. In this case, the butane gas mixes with oxygen gas to produce carbon dioxide gas and water gas or water vapor. So if you're asked, write the balanced reaction for the complete combustion of butane, and in this case you'd be given butane, C4H10, the complete combustion of that is going to be C4H10 plus oxygen to produce carbon dioxide and water. These are always the products of the reaction. It's always making carbon dioxide and water. Now I qualify that with it wants to make carbon dioxide. In a moment we're going to talk about incomplete reactions, which it doesn't quite have enough to make carbon dioxide. But for right now, complete combustion is taking the carbon-hydrogen chain molecule, reacting it with oxygen to produce carbon dioxide and water vapor. So we go through and look at this, and now we need to balance the reaction, right? This one might be a little bit too complicated to do with fractional coefficients and multiplying. We may have to do the matrix. But let's look at it for a moment here. We've got carbon. 4 carbon only occurs in one place, right? So go from 4 here, we got to go to 4 here. Correct? Hydrogen, 10. Hydrogen only occurs in one place. It's over here. I've got 10, and how many sets of 2 can I make from 10? 5. Now we've got oxygen, which occurs in 2 different places. So we've got oxygen recurs in 2 places. We have, looking over here, 4 sets of 2, which is 8, and 5 sets of 1, which is 5, to give us a total of 13. How do we get 13 out of sets of 2? 6.5. Now we need to go through and eliminate the fractional coefficients, right? So typically I would just go through it. Anytime I have a half, I just go through and multiply the whole thing by 2. It's not always the quickest, but it's a standard way to do it. And then we have to look at it again to see if we can reduce it. But let's multiply everything by 2, and we end up with 2 C4H10. I'm going to drop the phase symbols for brevity here, plus 13 O2 reacts to produce 8 CO2 plus 10 H2O. Does everybody see what I did? I just went through and multiplied every coefficient by 2 so that I eliminated the fractional coefficient. I went from 12.5 times 2, which is 13. Now every one of them has a whole integer coefficient. Yes, sir? This is my crossed 0, or crossed. Okay? And the reason I cross my zeros, the European zeros, is because of things like that. I differentiate between a 0 and an O. Like over here, it's 10H2O. All right. Now we would just take a quick look and say, can I reduce this anymore? Are there any common factors to these? Well, 13 is a prime number. 1 and 13 is all that goes into that, so no, there isn't. If you have any primes, we know we can't factor it out. So this is our balanced complete combustion reaction for butane. We take the molecule, carbon-hydrogen chain, react it with oxygen to produce carbon dioxide and water, and then balance it. Now the last reaction we haven't talked about yet is called incomplete combustion. Incomplete combustion happens when there is insufficient oxygen available for combustion. In the book, they give the example, let's see, if we go 2CH4, I'm going to try to stick to the examples in the book so you can refer back to them. The 2CH4, I'm going to, again, drop the phase symbols on these. They're not fundamental to it. Plus 3O2 reacts to produce 2CO plus 4 H2O. Now, I said before that complete combustion produces carbon dioxide and water. Incomplete combustion is where the combustion is taking place where there is not sufficient oxygen. There's not enough oxygen. See, in this one right here, we're assuming, okay, if I'm going to make this, and all I'm going to do is just add another over here on oxygen, I'm just decided, hey, I actually need 13. What are we assuming? That I can actually get 13. Okay? Here we're talking about complete combustion. And the reaction, if there's extra oxygen in the room, hey, it's going to keep reacting with complete combustion. This is the reaction that the chemistry wants to go to. It wants to form a complete combustion. But even though this is the balanced complete combustion, let's say that in the room itself, actually, though this would be balanced, there's just not enough oxygen. Rather than having, enough oxygen to run the full reaction, there's insufficient oxygen. And so though we might want to form CO2, we only get CO. Rather than getting carbon dioxide, a product of reaction, because there's actually not enough oxygen in the space, in the reactant space, rather than getting CO2, we get CO. Let's check this real quick for balance. 2, 2, 8, 8, 6, 4, and 2 is 6. Yeah, it's balanced. Just wanted to make sure. So what this is saying is, I recognize that if I had a complete combustion, it means that I actually, in my space, have enough of every one of these elements to support complete combustion. But if in the actual space there's not enough oxygen, the reaction will keep happening, but rather than producing carbon dioxide and water, incomplete combustion will produce carbon monoxide and water. Now, why is this significant to you and me, that we're getting carbon monoxide rather than carbon dioxide? Right. This one is a gas that you actually produce and exhale. When you breathe in a mixture of gases, one of the most significant being oxygen. The largest by volume is nitrogen, which is inert, which your body doesn't use. It just fills space, which is kind of cool. It dilutes the oxygen, so you're not always walking around hyperventilating. Okay? But you breathe in a certain percentage of carbon dioxide, but you breathe out a greater percentage of carbon dioxide. Your body is combusting all the time. You are a big engine. You are a giant combustion reaction. And you are taking fuels. You are taking carbon-hydrogen chains. And your body is breaking those down and adding them to the oxygen that you breathe in. And you're bringing in that oxygen, and then your engine system is sending out carbon dioxide and water vapor. When you breathe on a mirror and fog it up, or you clean your glasses, what you're doing is you're exhaling the exhaust from a combustion reaction in your body. Okay? So when you breathe in oxygen and you breathe out carbon dioxide, this is this normal reaction. So carbon dioxide isn't something that we fear in reasonable proportions. Of course, if you're breathing in a large amount of carbon dioxide, which means that you don't get enough oxygen, you're breathing in a waste gas and you're not getting your necessary fuel for this reaction. So yeah, it's kind of like putting the lid on a candle. It's gonna die out. So, but the point here being is you're not necessarily concerned about breathing in carbon dioxide because you breathe out carbon dioxide as well. Yes, sir.
Whenever you put the lid on the candle, all the oxygen inside the candle is replaced with carbon dioxide.
Mm-hmm. Actually, it's initially making carbon dioxide, but that's a good example. Let's stick with a candle example. Does everybody understand what we mean? Like one of those old Yankee candles, let's say you have a candle, like I have on my desk at work, and it's got a large thing, it's got a wick on it here, and you've got a candle burning in there, and it's tranquil breeze. So every time I go in there, I light it so I feel tranquil. And I've got a leaky window behind me, and I feel the breeze, and so together it's a tranquil breeze. Okay. So there's my candle burning, and in the room, with it sitting like this candle is taking in oxygen, and it's combusting the oxygen in a reaction here. Part of the carbon comes from the wick, and then you also have some gases being released from the wax, and the product of that combustion is water vapor and carbon dioxide. All right? Now, when I come over and I put the lid on the candle because I'm leaving for the day. The other day I had Audrey, my team leader for children's ministries, in my office, and I was leaving. I said, well, let me go ahead and put the candle out because I would hate for Mr. Jason to go in there later, turn off my heater, and put out my candle. You guys know Jason works at Shively as well, so we see each other when we leave here. I see him there a lot of evenings, too. And I know him as Jason, so forgive me, Mr. Parker. I forget that you're Mr. Parker here, you're Jason at work. Okay. Anyhow, So this candle's producing carbon dioxide and water, but the other day I went back and said, oh, Audrey, let me put out my candle. So rather than doing the whole thing real quick, right, and blowing it out, I just went over and put the lid on it. I covered it. Okay. So what I did right then is I captured the reaction space where the flame was at. And the flame, which previously had plenty of oxygen coming in from the room, was able to maintain complete combustion. But when I seal the lid, the candle will continue to make carbon dioxide until it starts to run out of oxygen. It no longer has the fuel that it needs to do the full combustion reaction, and so it starts to produce from the incomplete combustion. So inside here, where before it was making carbon dioxide and water vapor, when I seal it, and for a few moments when you seal it, the candle doesn't even seem like it's affected by it, right? It keeps on burning at the same intensity that it had before. During that time, it's still making carbon dioxide because it still has enough oxygen to fully burn. But you notice that there's a time between when it's fully burning and it starts to die. You see the flames start to get smaller, and it's not quite as robust, and it's starting to waver a little bit. That is the point where this reaction is running out of oxygen. And as it runs out of oxygen, it's no longer producing carbon dioxide and water. Because it has insufficient oxygen, it's now producing carbon monoxide and water vapor inside that space. Okay. And the reason is, it's not because it doesn't want to make carbon dioxide. The reason is it can't because it doesn't have enough oxygen. Now the next level happens. And even more, if you will, a more incomplete combustion is a third phase. And they have the reaction in the book CH4 plus O2 reacts to produce C plus H2O. Actually, 2H2O. Now look at what's happened here. Just looking at the reaction. I have something that, let's say it was reacting, producing CO2, but I seal it off. It starts to run out of oxygen. At a certain point, it can no longer make carbon dioxide because it's running out of oxygen, and it now starts to make carbon monoxide. And it continues to make carbon monoxide, and then eventually gets to the place where what happens over here? The flame goes out. And what's produced when the flame goes out? Carbon. Or just as fractionally before the flame goes out. Just fractionally before the flame goes out. It's not making carbon dioxide anymore. It's not making carbon monoxide anymore. The even further incomplete combustion is it's got so little oxygen that it's not even making a carbon-oxygen molecule anymore. It's just making carbon. Carbon is kind of like precipitating out, right? Carbon is becoming visible. And water vapor. You know this, right? You know this. Because whenever you look at a candle that's no longer burning, what do you see? The wick. How does it look? It's black. Where did that blackness come from? That blackness is elemental carbon. That blackness is that carbon right there that was produced fractionally before the flame went out, when the reaction was still taking place. That's why when the candle burns, the wick may or may not look black. But when it goes out, especially when it goes out because it's starved out, you see that carbon buildup on the wick. The carbon buildup comes from this incomplete reaction down here. All right? The primary stuff, the loose carbon, if you will. There's other things that are producing carbon in the burning of the wick, but in terms of the oxidation, or in terms of the combustion, excuse me, this is where it forms. So the principle here is, with this incomplete combustion, is that when the reaction space, when I say reaction space, I hope you'll understand what I mean. We have an enclosed system here. Whenever it was open, when the lid, before I put the lid on the candle, what was my reaction space? This is my room, the whole room. keep going out until it finally closes off. Well, I've got leaky doors, so it must be the hallway. We got leaky doors in the hallway. It must be the front. It must be the front door of the church. You got leaky doors at the church. Guess what? My reaction space was the world. But I come along and say, I'm gonna confine my reaction space now. I'm gonna shut it down, because as long as that's free and open, I'm gonna get probably plenty of oxygen coming in. But as soon as I make the reaction space confined and it's a closed system, now the oxygen starts to slowly get used up. And then the candle says, I'm fine. Ooh, getting hard to breathe in here. It starts to make carbon monoxide. Goes for a little while longer, says, you know what, I'm starving. I'm choked out. I quit. Boom. Makes carbon and some water vapor, and then the reaction stops. So incomplete combustion is this movement from making carbon dioxide to carbon monoxide to making carbon. Yes, sir?
How does blowing out a candle work?
It actually removes the oxygen altogether. Okay, that's why if you blow it too little, it fans it, but if you blow it more, it blows it out. You're actually taking the energy for the reaction and the oxygen away. For that microsecond, you're starving it, and it goes out before, the ability for it to receive oxygen comes back. Okay. One of the points they make in the book is about the use of a catalytic converter, and we talked about this in here before. 2 practical applications. How much time do I have, Mr. Parker? About 10 minutes? Okay. 2 practical applications. We've talked about it already. As a matter of fact, I have to admit to it wasn't even a guilty pleasure, but I was watching Wonder Woman on MeTV the other day, and they showed this thing where Diana was being murdered by a hitman because he took her into the garage, tied her up, left her on the floor, and left the car running. Okay, we've talked about that before, how if you want to be a hitman today, Hitman 101, it doesn't work anymore because of catalytic converters. A catalytic converter takes the exhaust from your car, and here was the thinking before, or this is what happened before. The way cars used to be designed, in order to have a good, robust combustion, you had to have the car moving. Okay, you had to have a certain amount of velocity, and as you slowed down, you were sometimes not getting sufficient oxygen into the engine to maintain complete combustion. As a matter of fact, when they want to soup up cars, what do? They put turbochargers, or they put blower fans on them. They blow more oxygen in, because blowing more oxygen in is blowing more oxygen on that candle or that fire that's about to go out, and you're that fine balance between blowing more on so it'll flare up and blowing too hard so you blow it out. So what would happen was the cars used to be designed that you had to have a certain amount of velocity in order to get enough air to maintain complete combustion. And what's coming out the tailpipe is mostly water and carbon dioxide. When you follow a car that's running and it's dripping water out the tailpipe, that water is condensed water that was created in combustion. Okay? So the car is moving at a certain velocity. It has enough oxygen coming into the engine, so the engine is producing water vapor and carbon dioxide because it's getting enough oxygen. But when you slow down, and particularly when you stop for an idle, you're just sitting there, the car's running but it's not moving, the cars used to not be able to get enough oxygen to maintain complete combustion, and the cars would then actually start to produce carbon monoxide. So whenever you'd be in your convertible in a traffic jam, everybody was getting lightheaded and sick because the cars were producing a lot of carbon monoxide. And then when they would get going again, it wasn't partially because you were moving and you had fresh air coming in, but partially because the cars would then start making carbon dioxide rather than carbon monoxide, and you weren't sitting in the poison anymore. That's why it used to be that you would take someone to the garage, you'd knock them out, and you'd turn the car on, and you'd leave, because the car running in a closed space would be producing carbon monoxide, a poison, and the person would eventually die from the poisoning. But then they came along with the catalytic converter. What a catalytic converter does is it chemically takes, whenever the engine produces carbon monoxide, and because of efficiencies in the design, they tend to not run out of enough oxygen to a much more severe point, usually when they're very much out of tune and things like that. There's usually something mechanically wrong for your car to get to the place where it will produce carbon monoxide. But even if it does produce carbon monoxide, the catalytic converter chemically reacts with the carbon monoxide and converts it into carbon dioxide. So even if your engine makes carbon monoxide, the catalytic converter changes it into carbon dioxide. Okay? This used to be a problem too. Now you might see ventless fireplaces. And they give this example in the book too. A ventless fireplace, it's a fireplace that actually operates in the middle of a room with no chimney, with no exhaust. My parents had one of these in their bed and breakfast in upstate New York. It was a gas fireplace in the room, and it just sat there and burned with a flame, but there was no chimney because it was so efficient that it was able to burn and produce carbon dioxide and water. But here's one of the things, too. As we get more and more able to take houses and make them really airtight, to make sure they don't leak, the windows don't leak, and the walls don't leak, and they basically have like you're living inside of a Ziploc bag because air can't get in and out. One of the things that used to save people was even if you had something happening in your home and you had incomplete combustion happening, whether it be at a ventless fireplace or possibly at a water heater or some other place where there was a flame, even if you were running out of air in that space or oxygen in that space, the walls were leaky enough that oxygen could be pulled from other areas and keep it making carbon dioxide. But because now we're so airtight and so efficient, we no longer have leaky walls and leaky windows, which is good if you're trying to keep the place warm, but it's bad if you have a combustion gone wrong in the house because you can actually starve yourself of oxygen, and the heating element can start to produce carbon monoxide rather than carbon dioxide, and you can actually poison yourself, which is why you have carbon monoxide detectors in your homes. Back log cabin days, you couldn't stop the breeze from coming in, which meant you were cold, but your fireplace wasn't going to kill you because you were making carbon dioxide. Now, we will die nice and warm because our walls don't leak, but inefficient combustion will produce poisonous gas that will kill us. So the deal there isn't that the carbon monoxide gets to leave because the house is leaky. The leaky house will keep the combustion from forming it in the first place. Okay, so you see the difference there? In terms of combustion and incomplete combustion, complete combustion is a carbon-hydrogen chain reacting with oxygen to produce carbon dioxide and water. Incomplete combustion, the principle is I don't have enough oxygen to do that, so I fall back to producing carbon monoxide rather than carbon dioxide. And in its most severe form, I no longer even make a carbon and oxygen molecule, I now just make carbon and water vapor because I'm starving out the oxygen.